Welcome everyone. For today's prep, we're going to be looking at cylindrical coordinates and specifically how to use these to help us integrate certain types of triple integrals. So first of all, let's just start with what is this coordinate system? And it really inherits a lot of it from polar coordinates. So when we looked at polar coordinates for the xy plane, we use the standard equation x equal to r cosine theta and y equal to r sine theta. And it's the same deal for cylindrical coordinates. Now we're just adding a third dimension, z, and this is just the height. So the two of our variables, usually x and y, these are just regular polar coordinates using our standard equations. Our third variable, usually z, represents a height. And that's the way we want to think of this. So we're going to let our z coordinate, it's just the height above, in this case, the xy plane. So we want to think of our z coordinate as the height above the xy plane. So we're going to, essentially with cylindrical coordinates, we're converting x and y into just standard polar coordinates, and then z is just z. And so we have our usual equations, x equal to r cosine theta, y equal to r sine theta, and now we have this third coordinate z, which is just the height. And we can also convert using our standard r squared is equal to x squared plus y squared, and tan theta is equal to y over x. And, usually z is equal to z. So what does this look like? So these are the same equations that we were using with polar coordinates. So what does this look like? Well, here's a little graph. Let's just see an example. So we have our point P. Let's look at this point P sitting in three-dimensional space. And let's say it has coordinates x, y, z. Regular rectangular coordinates x, y, and z. Well, we can convert this into cylindrical coordinates, and the cylindrical coordinate representation for this would be r theta z. So the z coordinates would be the same for this. And again, it's just the height above the xy plane. Now, what does r and theta represent? Well, they're kind of the usual polar coordinate terms. So r, well, it represents, if we kind of look at the shadow of this point on the xy plane. So we have this point x, y, 0. So this is the shadow of point P sitting on the xy plane. R is just the distance between that point and the origin, kind of like standard polar coordinates. And theta is the angle between the positive x-axis and the ray extending from the origin through that point. So theta measures this angle right here. And that's really it. It's cylindrical coordinates is just polar coordinates, and then we're throwing in some height to it. And for a little practice, we'll look at the first example here. We'll look at part A of the first example. So let's plot the point with cylindrical coordinates 2, 2 pi over 3, 1. And we want to find its rectangular coordinates. All right, so first of all, when we're plotting in polar coordinates, a lot of times we want to start with the theta value. So again, the theta value here, so when we look at this, we have our r value, we have our theta value, and then we have our z value. So we have r equal to 2, we have theta equal to 2 pi over 3, and then we have z equal to 1. So these are our cylindrical coordinates here. And when we plot in polar coordinates, usually we want to start with the theta value. And so for theta 2 pi over 3, well, if we look at our our x and y plane, we want to think about this just on the xy plane for now. And where would the 2 pi over the theta equal the 2 pi over 3 reg sit? Well, we have our positive x-axis. So that is theta equal to 0. We have our negative x-axis going back this way. So that would be theta equal to pi. We have our positive y-axis kind of extending this way. So that is theta equal to pi over 2. And then 2 pi over 3, what we're doing is we're kind of looking at, we're slicing up this angle pi into thirds. So we have our pi thirds angle, which would look something like this. So this is 1/3 of this angle here. Then we have 2/3, and then we have 3/3 taking us back. Now we're looking at theta equals 2 pi over 3, so we just want the 2/3. So this would be theta equal to 2 pi over 3. So we find the 2 pi over 3 ray on the xy plane, and then we count out 2 units away from the origin. So r is equal to 2, so we count out 2 units in that direction. That tells us where this height is, and then we go up 1 unit in this case because z is equal to 1. So we kind of use theta to figure out the direction. Then r tells us how far we go in that direction, and then z tells us how far we go up. So r is equal, it's hard to read, r is equal to 2, and then z is equal to 1. So that tells us the vertical. Now, and that gives us our point P. Now we can convert this into regular rectangular coordinates using those formula. So x is r cosine theta, y is r sine theta, kind of our standard polar coordinate stuff, and z for cylindrical coordinates is just z. So if we plug everything in, the r value is 2, so we get x is equal to 2 times cosine, and then we plug 2 pi over 3 in for theta. And then we do the same thing for y, so 2 times sine of 2 pi over 3. And then our z coordinate here is just 1. So good old z is whatever our z value is. And if we simplify, cosine of 2 pi over 3 is negative 1/2. So we end up with x equal to 2 times negative 1/2, which is negative 1. And then sine of 2 pi over 3 is square root 3 over 2. So we end up with our y value is 2 times square root 3 over 2. And then z is nice and easy. And if we clean it up, we can write down our coordinates for point P. So the x coordinate was negative 1, the y coordinate was 3, and then the z coordinate was 1. So we can think of this point in either rectangular coordinates, or we can think of it in cylindrical coordinates. All right, so where we're going to be using cylindrical coordinates is to help us with integrating certain types of triple integrals. And we're going to skip ahead. We'll come back to this in class. But the types of triple integrals we're going to be looking at are when we have this solid E. So we have this region E. Sitting in, here's our x-axis, our y-axis, and z-axis. So it's sitting in three-dimensional space. It's a three-dimensional object here. And when we look at the shadow of this object on the xy plane, we have this region D. So we're looking at the shadow. And where we usually want to use cylindrical coordinates is if this region D is best described using polar coordinates. So if region D is best described with polar coordinates, then we want to use cylindrical coordinates. All right. And the reason for this is because we're going to be able to, well, convert the limits of integration, and it might simplify down the integration process for us. And we'll see that in an example. So when we do this, we can think of our triple integral. So if we have the triple integral over our region E of some function f of x, y, z, with our three-dimensional differential dv here, we can think of this as an iterated integral where we have a double integral over region D, and then we're inside of that we're integrating the function f of x, y, z with respect to z. And we're integrating this function, if we're integrating with respect to z, we're integrating between the bottom surface, the equation for our bottom surface, and then our top surface. And on our little sketch here, we have our top surface here, so the top of our solid E. And then we have our bottom surface. That gives us the bottom edge. And cylindrical coordinates, if we're integrating with respect to z first, well, with cylindrical coordinates, z just stays z. So there's not too much that happens here. We are going to have to convert x and y, and then any of the x and y's that we see in our limits of integration here. But then we convert this region D into polar coordinates. So we're kind of doing this in two steps. We have this inner integral in terms of z, and for cylindrical coordinates, z just kind of stays z, and then we convert region D into polar coordinates. And we've done an example like this already, but now we're just kind of giving a name to it. And so when we actually have a triple integral and we want to just go all the way and convert it to cylindrical coordinates, we have to do a few things. So we have to, first of all, convert the function that we're integrating. So all of the x's all the x, y's, and z's that we see in our function, we have to convert those in the function we're integrating. And we're using our standard conversion. X is equal to r cosine theta, y is equal to r sine theta, and then now we're throwing in a third variable, z just stays z. So it's kind of nice. So we're just doing polar coordinates, basically. Then we have to convert our differential. So that's the next thing we have to do. So our triple integral differential here, dv, we're going to convert it. And the conversion here is r dr d theta, so our regular conversion for polar coordinates, and then just, again, z stays the same. So the differential for dz just stays the same. So we also convert differential. That's a big one. Don't want to forget the differential. Something small, but it makes a difference. And in this case, the conversion here is very similar to polar coordinates. So our differential dv becomes our polar coordinates, r dr d theta, and then dz is thrown on. And normally we do our z integration first, so that's the first differential that we write. But, sometimes we might, change the order around. So we have our regular polar coordinate and then dz. And then the last thing we do is we convert our limits of integration. So we don't want to forget about our limits of integration as well. So let's give this a try. See how this works. So let's look at example 4. So we're going to jump ahead. We'll look at example 3 in class, but let's look at example 4. So we're going to do this triple integral. And as it's described right now, what are some tells that we might want to use cylindrical coordinates? Well, I see a whole bunch of these x squared plus y squareds. So that's kind of the first tell. That would be really nice if we could say that's equal to r squared. That would simplify this down. But really where this comes in is we want to start by looking at the region D. So really where polar coordinates can become helpful is if our region D is better described using polar coordinates. So let's think about region D. And the way we get region D is we look at our last two limits of integration here. So we're integrating with respect to z first. So we'll come back and deal with that. But let's look at dy and dx. So our differential dy means y is kind of varying in between these two curves. So let's actually sketch what this looks like on our xy plane. So usually it's helpful to picture what this region D looks like. And the square root of y equal to the square root of 4 minus x squared, that's the top half of a circle of radius 2. So this is y equal to square root 4 minus x squared, and it's going from -2 to +2 along the x-axis. So that gives us the top half of a circle. Then the negative square root, well, just gives us the bottom half. Okay, so we know y is in between these two curves. So if we draw our cross-sectional cut, we know that the top curve is the top part of this circle, and the bottom part here is the bottom part of our circle. And then we look at our limits of integration for x to see how far back and forth we kind of go. And so we see that we go all the way to this point right here, all the way to the extreme end of our circle. And then that's where we start. And then we just shade in this entire region. And we stop at x equals 2. So we cover up the whole circle. So this is our region D, where we're going from x equals -2 on the left to x equals +2 on the right. And we have our positive and negative square root functions that are giving us the top and the bottom edge. All right, so this is our region D. We've sketched it based on what we have from our two last limits of integration. And now this is part of a circle. Well, it's actually entirely a circle. And so it's better to use polar coordinates. So now we want to think about what is region E. What's our solid E? And let's describe this in cylindrical rather than x, y, and z. So we already have the description in terms of x, y, and z. Let's convert this into cylindrical. And so to do this, we're going to be looking at the set of points. So E is going to be the set of points r, theta, z, such that, and now we want to think about, first of all, what are the r values that give us this entire circle all filled in? Well, if we draw a ray, kind of starting at the origin and extending through our region and out, the smallest r value we can get is when we're right at the origin, so that's r equal to 0. And then the largest r value I can get before we're out of our region is right there on the edge of the circle, and that happens when the radius is 2. Okay, so our r values are between 0 and 2. Then we want to imagine how far we can rotate. If we start on our positive x-axis here, how far can I rotate this around before I either leave the region or I start to overlap? And I can go all the way around the circle here until I get back to the positive x-axis. So all the way around means theta is between 0 and 2 pi. That gives me one full cycle around the origin. And then the last thing we want is an inequality for z. So we want our z inequality. And we see that for z, the largest value z gets is 2. So perfectly fine. That can just stay 2. But the one thing we do have to worry about is we don't want x's and y's anymore if we're describing this in cylindrical coordinates. So when we see this square root x squared plus y squared, we want to do something with that x squared plus y squared. And we just note that x squared plus y squared is equal to r squared when we're converting back and forth between rectangular and polar and cylindrical coordinates. So if x squared plus y squared is r squared, well then this becomes the square root of r squared, which is just r. So that was the only thing we had to kind of worry about there, is we needed to do a little bit of rewrite for this solid E. All right, so now we have our description for E all in cylindrical coordinates, and we're ready to we're ready to convert this over fully into cylindrical coordinates. So let's write it out. Our triple integral over this solid E of the function, what's our function? Well, our function is x squared plus y squared. All right, so we got to do three things. We've already done the work getting our limits of integration changed. So that's pretty much done. We also have to convert the function we're integrating, and then we also have to convert that differential. Make sure everything gets into polar coordinates. So again, x squared plus y squared, we can use it again. That's r squared. So we get a copy of r squared there. And then we want to convert the differential. So the differential from rectangular to cylindrical coordinates is going to be our usual r dr d theta. But now we just want to make sure we have one extra one, and that's the differential dz. And we're going to be setting up our integral, and we're going to do the integration for z first. So I'm going to put the dz there first. All right, so now we throw in our limits of integration that we found. So z is between r and 2. So we're going to go from r to 2. Then I have dr. So on the middle one, we're going to put our limits for r, which are 0 and 2. And then last I have d theta, so I'll put the limits of integration for theta. So we're going from 0 to 2 pi. All right, so we worked with our function, and then we also converted our differential and our limits of integration. All right, so now we're ready to do it. So let's combine the r terms. R squared times r is r cubed. And when we look at this, we have to do the z integration first. And the reason is because the limits of integration, one of the limits there has an r in it. So we actually have to do the integration for z first. And so when we do that, we get r cubed, and the integral of r cubed would be r cubed times z, and then we just plug in the bounds. So when we do our z integration, we should end up with r cubed times 2 minus r. Top limit minus the bottom limit. All right, so once we finish the z integration, now we can actually, these limits of integration are all just constants. Our function here only has r's in it, so we can actually use Fubini's theorem again, separate out the r and the theta, and write this as just a product. You know, don't have to do this. Kind of makes it easier sometimes. So we could do our integration 0 to 2 pi d theta times the integral from 0 to 2 of the r terms. So 2r cubed minus r to the 4th dr. And if we finish this up, the integral of d theta from 0 to 2 pi is just 2 pi. And then for the r terms, we end up with 2 over 4 r to the 4 minus 1 over 5 r to the 5. And then we're just evaluating that from r equals 0 to r equals 2. And if we do the evaluation and clean this up, we end up with, 16 pi over 5. All right. And we can see for this, what we were doing is we were integrating. Our region E here was the region bounded on the top by the surface z equals 2. So that's just a horizontal plane. And then it was bounded below, the bottom surface here was z equal to that square root function, which is just gives us this cone. And so we're looking at the solid in between that kind of flat top and this conical structure. And if we look at the shadow that this casts onto the xy plane, the shadow of our solid was a circle. And that's what kind of motivated our use of cylindrical coordinates. All right. So we're going to try another example like this in class. And, well, maybe we'll also, we might jump ahead. Who knows? We'll see. But we're also going to look at spherical coordinates. So cylindrical coordinates help when our region's kind of circular. And spherical coordinates, well, we'll see what that is. So we'll see you then. Bye-bye.